Well, hello world, all you processing users out there. This is a new video tutorial by John Park, and today we're going to be talking about for loops. Now, for loops are a very important type of loop that you're going to be learning and working with through many different programming applications and situations. So let's talk about a couple of those situations, like when might you use a for loop? And once we get into that, then we'll talk about the anatomy of a for loop and then actually create some and get comfortable with them. So a for loop works by going through a loop, a circular kind of loop where you're going to be going through, say, looping 10 times. And a loop can go through 10 times, and every time it goes through the loop, it can do an operation. So, for example, you might have a giant list of words. Let's say you're creating a word-based program, and you have not just 10 words, but maybe you have 1,000 words that you want to go through. What if you wanted to see if one of those words happened to be the word icky, which, hey, looks like we do have the word icky. If you wanted to check the word icky against a giant list of words, you'd probably want to cycle through every single one of those words and check each one for whether or not it is equal to icky. Another example might be, let's say you made a program that's a card game, a memory-based game, and you're going to be essentially drawing a giant grid of cards. Well, it's kind of a pain in the butt to say, all right, I want a program that draws this one here, and this one here, and this one here, etc. Why not just have a program that will go through and say, hey, all right, for every 50 pixels across, I want you to draw a new card, which will essentially make one row. And then, hey, if that row fills up, I want you to drop down to the next line and start over and do the next row. Drop down the next row. That's a really efficient thing to do using for loops as opposed to draw every single card with its own line of code. And another example when you might use something like a for loop would be when you're doing something like video tracking. All right, what if you're looking at an image from a video camera or webcam and you want to see, hey, is a certain pixel of a certain darkness or a certain color against a different background? This is used all the time for doing things like tracking bodies in space or tracking for certain colors. So, 3 different examples of why you might use a for loop. So now let's actually get into what a for loop looks like. Well, I'm just going to start with the basic program, do the void setup and the void draw. And this is the basic anatomy of almost any processing program. And in the void setup, I'll go ahead and create a size. I'll just do 900 by 600 pixels. And in the void draw, I'll go ahead and just do a background call. Remember, that'll draw a blank color, and I'll just put it in 0 to make that black. Okay, so in terms of how a for loop works, is there's a very specific anatomy or kind of way to write a for loop. I guess the official term for this would be syntax. This is the way in which the code has to be written. And it is always going to start with the word for. So I'll type in the word for, open a parentheses, and there are 3 parameters that it's looking for. The first one is the starting condition. The second one is up until what point will this loop run? And the third condition is every time the loop runs, what changes about it? So it's very typical to start by declaring a variable. So the first part will say int I equals 0. Okay. Now to tell the program that the first parameter of that for loop is finished with, we're going to put a semicolon, not a comma, a semicolon. So the second part is how long will this loop run? And so we'll say as long as I is less than 20, and then a semicolon. And then the final and third part is what changes each time the loop takes place. And I'll say I++. Now I++ just means whatever I used to equal, we're going to add 1 to it. Okay, so if I begins at 0, and then we say I++, then I grows to 1. And then I grows to 2, and then 3, and 4. This is called incrementing, to increment by 1 value beyond what it used to be. By the way, you could say I minus minus. That works just as well to start at a value and shrink it by 1 value, or 1 number. But for now, I++ works. So now I'm going to close the parentheses that we opened up over here, and I'll open a curly bracket, drop down 2 lines, and close a curly bracket. So this is really the basic anatomy of any for loop. These 3 parameters can change, but in this case, what we're saying is, hey, I want this thing to loop 20 times because I starts at 0 and goes all the way to 19. Once I hits 20, I is no longer smaller than 20 if I equals 20, and so the condition will no longer be met and this loop will end, and it will kind of stop running and continue back in the normal void draw. So let me show you an example of how this might work. If we wanted to draw, say, an ellipse, and I'm actually going to do this, I'll just cut this. If I wanted to draw an ellipse, I would type ellipse and open a parentheses and say, hey, what are the x and y coordinates of where the ellipse goes? I might say 50 pixels over, 50 pixels down, and I want the ellipse to be a 20 by 20 pixel width and height ellipse. So the x position, y position, width, and height are the 4 parameters of an ellipse. If I draw that, or run the program, let's just see how it looks and what it does. Hey, there we go. I bet we love our ellipse. It looks great. But, hey, if I wanted to draw 20 ellipses in a row, sideways, well, I guess we could copy this and we could paste this down here. And if I want to have them be side by side, I have to change the x position of each one. So I could change the next one to 70 pixels and just make sure that one runs. All right, we've got 2 side by side. And I could just keep on doing this 20 different times and just keep on changing each one of these values. And boy, you know, that really gets boring and tedious. No fun. So instead of doing all that work, why don't we instead put this ellipse inside of a for loop? Okay, well, hey, look, I happen to have my for loop. So I accidentally erased it. So int I equals 0, I is less than 20, I plus plus. And so now, when I have my 2 curly brackets for the for loop, what this is going to do now, if I just run this program, is it will actually draw 20 ellipses all right on top of each other, because they're all located at 50 pixels over, 50 pixels down. So we won't really see any difference, but hey, there happen to be 20 just all on top of each other. What if I want to spread those out? Well, we know that the x position is what's going to be the factor that determines the location of the ellipse on the x-axis. So we need this x-axis to change. Maybe we want it to start at 50, but then we'll have it grow by 25 extra pixels each time. Well, this is tricky because we're only calling the ellipse once here, and it's happening in a for loop, and this loop is going to loop, essentially draw 20 ellipses, and then it's going to kick us out of the for loop and repeat all over again. So the secret and the most powerful thing about using these for loops is each time the for loop runs, I is starting at 0 and I grows one number at a time because that's what we've set it to do. So the first time in the loop, I is 0. Next time in the loop, I is 1, I is 2, 3, 4, all the way to 19. That means that each time when I grows, we can use the letter I as this growing value in between the 2 curly brackets. So since we know I is going to go between 0 and 19, what if we take the x position of the ellipse and add to it something involving I, because we know I is going to change. So if we just say 50 plus I, well, this will cause a kind of an interesting thing, because that means every ellipse that it draws, every one of those 20 ellipses, will be just 1 pixel to the right of the last one. So I will start at 50 and then become 51, 52, 53, 54, all the way to 69 pixels over. It won't look great, but here we can kind of see the streak of ellipses. All right, if we want to spread that out even more, which I think we should, what if we say I times 25 pixels? So if you think about the math of what's happening here, the first time around, I is 0. So 0 times 25 equals 0. Plus 50, that means the first ellipse will draw at 50 pixels over. The second time I equals 1, so 1 times 25 is 25. Plus 50 equals 75. And so that means the whole ellipse shifted over 25 pixels. Each one will do that. All 20 of them will be 25 pixels to the right. So let's run it. Hey, look, there they all are, shifting all to the right. So we're very quickly making a whole row of these pixels, or of these ellipses. Let's say we wanted more than 20. We wanted 80 pixels, or I'm sorry, 80 ellipses. We'll go ahead and run that program. And look, there's so many that are spilling off the side of the page. So once you get this basic kind of format of using a for loop, boy, you can do a lot of stuff. So let's push this even further. Let's say for my ellipses, remember the third and the fourth argument are the width and height. So it's currently set to be 20 pixels wide. Let's make this really small. We'll say 6 pixels wide, 6 pixels high. And up in the void setup, I'm going to say no stroke. And what that's going to do is it's going to remove the outer black outline, which is the default stroke of our ellipses. So now we'll just get that white fill. And I'll run this. We get lots of little dots. Now if we want them not to be spread out as far apart, remember that's what this I times 25 thing was doing. Because I made all the ellipses smaller to be 6 pixels wide and 6 pixels tall, then we can pack them in tighter. So let's say we only move them all 10 pixels apart from each other. And now, since we have 80 of them going, there we've got 80 shooting all down in a row. So, for the sake of being clear and potentially redundant here, let me explain this one more time in case there's anything unclear about this. In our program, when we first start running this, okay, the void draw starts. Remember, void draw is a type of a loop. It's just constantly going to go through these every single frame. So we're going to call a background, which cleans the slate. It's essentially like a big black splash of paint that hits the whole canvas. And then right away we start into this for loop. And the for loop starts by saying, hey, I want to create a new letter, it's a new variable called I, and I'll set it to be 0. So right away, I is equal to 0. Now this loop is going to run as long as I is, in this case, less than 80. And this is a value you can change. That could be 10, and the loop will only run 10 times. Or it could be 8,000, and it'll run 8,000 times. So now this is going to run, as long as I is between 0 and 80, it will run. And every time one little iteration of this loop happens, I will grow by 1. So I++ is the same thing as I equals I plus 1. Those two statements are identical. So that means this loop will run 80 times. Now, when it runs 80 times, it'll just kind of get stuck in itself here, as long as I is less than 80. When I is no longer less than 80, when it becomes 80 or larger, then the condition is met for this loop, and it's done. It finishes itself. And when it's done, then it keeps on going to the next line. Nothing's happening here. We hit the end of our void draw, and then whoosh, we start back again in the void draw loop. It begins going all over again. Black background, new for loop, etc. So I guess the key to remember is that the for loop will kind of get stuck inside of these two parentheses until, for as long as this condition is true. When that's no longer true, then we'll get kicked out of the for loop and keep on doing our other stuff. Great. So we have a set of little ellipses here. That's just a one-dimensional row. It's essentially a line. Let's say you want to make a whole grid. Okay, so we have essentially one X row here. What if we want a bunch of these that move down as well? Well, we can do that. One way to think about this would be, what if we have a loop inside of a loop? Okay, so we know that this guy right here is drawing us one row, but what if we have a different loop that this one is inside of? So we're going to nest this for loop inside of another one. And the second loop will essentially just be moving this whole thing downwards. So when one row is done drawing, then I'll skip us down to the next row and the next row down. So it's going to make us a series of stacked rows. So let's try it out. So I'm going to make a little note for myself by commenting. I'll say, this is a row across. Okay, and I'll just kind of clean this up here. Now, if I want to make a bunch of those rows, well, hey, I can make another for loop up here. Now, because we're going to have a for loop inside of a for loop, it's really important that we do not reuse the same letter I here. And that's because if we did recycle it, we'll set this I to 0 and it kind of grows. But then I gets reset to 0 here again, and that becomes a problem. So you can choose another letter. I'll choose K. So int K equals 0. K is less than, and I'll just say 40. K plus plus. Okay, this should look pretty familiar. Those are my three parameters, and now I make sure and open a curly bracket. And I actually want to close this curly bracket after this for loop is finished. All right, so I'll just close it down here. So by doing that, and I can space this out if that makes it a little bit easier to understand. Now we're starting with this for loop that's going to run 40 times, but for each iteration, for each time this for loop begins and kind of runs, inside of that, it's going to run another little for loop which will run 80 times. So K is 0, and then this for loop runs 80 times. Now K is 1, and then this for loop runs 80 times. Then K is 2, all the way down to 40. So now that we've got that going on, if I were to run this program, oops, I forgot to say int K equals 0. When I run this program, it's going to look exactly the same, because we've got 40 of these rectangles that are all drawing right on top of each other, or 40 of these rows that are all drawing on top of each other. So we essentially need to space these out in the y-axis so they're no longer all sitting on top of each other. So remember, we've already spread them out in the x-axis during this first parameter of the ellipse. Let's go ahead and hit up this second parameter because this is the y location. Now, we want to spread this out based on which row we're talking about. Now, we're doing that 40 times by using this letter K. So let's go ahead and use the letter K down here. And we're going to follow the same type of idea that we did to spread them out horizontally. So we can say 50 plus K times 10. So the first time this main loop runs through, K is 0. So 0 times 10 is 0 plus 50. So that means all of these ellipses are going to be located 50 pixels down. The next time around, K equals 1. So now 1 times 10 is 10 plus 50 becomes 60. It'll spread them down 10 pixels down. So let's go ahead and check it out. Boom. There we go. We've got this nice big grid of different ellipses going on. Now, what if we want to add more? Well, we can just go ahead and change it from 40 rows to 70 rows. Rerun. We've got a lot more drawing here. So this is kind of a very impressive and efficient way to do a lot of something many times just by using a couple lines of code in using for loops. And in this case, if I want to have an XY grid, we can put a for loop inside of a for loop. So the first one is responsible for essentially the y-axis placement, or moving them up and down vertically. And the second for loop here is for the x-axis, to make each individual iteration, each arm or row that spreads the ellipses out horizontally. All right. So what else can we do with this? We've done a lot of kind of nice work here. Well, let's space things out and change it up a little bit. So instead of running 70 or 80 across and 70 down, let's just change this to say 30 across and 18 down. Okay, and in terms of the spacement, now that we have fewer of them, we can space them out more. So let's say I change both these to 25 and 25. So there's still going to be these little 6 by 6 ellipses, 6 pixel by 6 pixel ellipses, but now they're going to be spaced out 25 pixels apart. And let's see how that looks. Okay, that's not bad. We'll go just a little bit more in the x-axis. So we'll spread them out to 30. And we'll run that. Okay, and then the y-axis, we'll try 30. There we go. And so when we run this, boom, it spreads them all out. So the reason why I'm kind of spreading this out is I want to show you very quickly, hey, we don't have to really draw these as ellipses. Let's draw them as little pictures instead. So I'm going to go ahead and create, or go to just a web browser, and I'll go grab a picture really quickly. So let me go ahead and go to Google Images, and I'm going to grab, oh gosh, I don't know, a picture of a kiwi. And I'm going to grab one that's a transparent PNG file. And a PNG is just a file format that allows for a transparent background. So let me go grab this. And I'm going to call this Kiwi. And in my processing program, before I work with imagery, I need to make sure and save this thing. So I'm just going to do a file, save as. And I will pull this right into, where I'm saving this whole file. For loop video. And I'll call this my loop. Okay, so now that means it creates a new folder in there called loop. Now how it works with images is we need to go ahead and save our image inside of a folder called data. So I can make a new folder here, call it data, and then inside of that data, that's where we're going to drop in our image file. So mine's called kiwi.png. So in my processing sketch, I need to start to work with imagery. Now if you're not familiar with this, or if you're a little rusty, the search term to really look up is something called p-image, or that stands for processing image. So you say p-image, give it a name, I'll call mine just kiwi. And then down in your void setup, we need to load in that file into this thing that we called kiwi. So I'm going to say kiwi equals load image, open parentheses, and in quote marks, put the name of your file. Mine was kiwi.png. Close parentheses. Close the quote marks. Okay, so now that we've done those two phases, as long as there's an image called kiwi.png inside of the data folder of this loop file, then whenever we reference kiwi, we should be good to go. And it should pull up that picture. So I bring that all up because, hey, we are actually drawing our ellipses here, but we could also be drawing kiwis instead. So let's try, right after we draw these ellipses, let's now say image. And whenever you say image, then you want to put the name of the p-image that you created. So I called mine kiwi, I'll say kiwi here. Now it wants the x and y location of where these are located. Well, hey, guess what? We have the x and y location of where our ellipses are being drawn right here. I might as well grab that, paste that in there. Okay, and let's go ahead and run this and see. Wow, we have a lot of kiwis. Now the pictures of the kiwis are way too big, and also the top left of the picture is what it's thinking it of as the orientation point, or 0, 0. So let's just change that part first. So in the void setup, if we want all these pictures to draw from its center point, there's something called image mode, like this, and then you put an all in caps center. That means when it draws the pictures, it will draw them with the center point, the logical center of the picture being 0, 0. So that all looks good. We've got tons of kiwis. They're all too big. Now you could go into Photoshop and resize them, which would be smart to do. But since my kiwis aren't way too big, they're just a little bit too big, I can actually, in the image call, where I have the first parameter is the name of the p-image, the second parameter is the x position, the third parameter is the y, you can add a fourth and a fifth parameter to the kiwi, or any image call, to change to essentially rescale the image to a certain width or height. So let's say I change this to be 15 pixels wide by 15 pixels tall. That's going to shrink all my kiwis down, and now I've got lots of cute little kiwis. And if actually that looks a little small, let me change these to 45. 3 times bigger. Okay, so there we go. We've got a lot of them. So the nice thing is we're just kind of borrowing all the work we did with our ellipses here and just using the x and y position of them to put the kiwis in. What else could we do? Well, let me show you one more interesting little trick. Which is, what if we didn't want a whole grid of these kiwis, but instead you wanted to make a circular array of them? If you wanted to kind of have, let's say, 20 copies, and each one rotates by a little bit more to make a certain visual kind of pattern. Well, let's try this. let's get rid of the ellipses. And I'm actually going to get rid of one of our two for loops, okay? Because we don't need a nested for loop for this. The nested for loop was only to get that XY grid of these. Instead now, I'm going to be drawing these kiwis, and I'll start with them just in a line. So right now, the kiwis, I've got 30 different copies, or 30 iterations drawing of this image. And so I'm just going to, for now, put these all... spread them out horizontally, but in the y-axis stick them all at 100 pixels down. We'll just run that. Okay, there we got a bunch. 30 might be too many. Let me just start with 10. I'll spread them out a little bit more. So 30 pixels across. Let's try 50 pixels across. Okay, so 2, 3, 4, 5, 6, 7, 8, 9, 10. And they are 50 pixels across, starting at 50 pixels over. So when I say 50 pixels across, I mean 50 pixels between each copy. Okay. Now what if I wanted these kiwis to rotate? Now there are a couple different things we could do. We could have them rotate around themselves, around their center point, or we could have them all rotate around kind of a bigger middle section. So when we start getting into rotation, some interesting things come up. Whenever you run a program, and I'll just pull this one up here, if I were to tell these to rotate, they would always want to rotate around the origin point of your sketch. And the origin point is also what we can think of as 0, 0, or the top left. I'll show you this in a moment here. So, you can always rotate something by just using the word rotate. And I'm going to do this above the for loop. So before the for loop gets called, I'm going to call the rotate. Rotate, open parentheses. Now this means everything in the for loop, or that whole line of kiwis, they're all going to rotate together. So kind of like an arm, all right? So under the rotate here, you might think, well, I could put in 12. I want it to rotate 12 degrees. Well, that would almost work, except for processing things in terms of radians, instead of degrees, and radians are another way to measure rotation. So 2 times pi radians is equal to 1 full circle, or what you might think of as 360 degrees. If you don't want to deal with radians, there's a very nice way to convert degrees into radians by just saying radians here. So now I can put in a degree base value. It will then convert them to radians, and then it'll rotate by that many. So let's say I want to rotate this by 22 degrees. And I run this. Okay. So it actually took from the top left, or origin, it took the whole sketch, and as if it was one big piece of paper with a thumbtack in it, the top left, it rotated this whole thing 22 degrees down. What if you want it to constantly rotate? Okay, well, that means instead of having a static number here, we need a number that's going to grow or change over time. Well, let's try something like that. We're going to make a new variable that's going to hold a rotational value, and that will change over time. Now, I could put in an int here, but that would be an integer, and that would mean it could only rotate by whole numbers. Instead, we'd like something even smoother, so we could rotate by, say, 1.28 degrees instead of just 1 degree. So instead of an int, we're going to call a float. And a float is a floating point number. It can be a decimal base, and it could be negative. It has a kind of a lot more range than what an integer could be. So I'm going to call this float rotator. All right, actually, let me just call it r value. That's even easier to remember. So r value equals 0. We're going to start this value out at 0 and tell it that it's equal to that to begin with. Now down in the void draw, we want this thing, r value, since this is going to hold a rotational value, we want it to grow over time. So we can always say r value equals r value plus 0.1. Okay, now there is a faster way to write this, but I think this is a little bit easier for beginners to understand that we're going to take the old value, r value, then essentially new value, r value, is equal to the old one plus 0.1. every time this void draw runs, our value will grow by this much, which isn't very much, right? 0.1 degrees. So now that we have that, let's swap out the solid number of 22 with the thing we just made called R value. We'll go ahead and run this program. Okay, now we can really tell that it's choosing this top left part of the sketch to rotate around. And there go our kiwis, rather slowly. Hey, if you want them to move faster, why not have the number that R value is growing by be bigger? 0.7. This should be 7 times faster. Whoosh. Okay, now you can do some kind of fun stuff. If I were to get rid of my background or just move my background value to the void setup, it'll only draw black once. And then in the void draw, it'll just leave the old stuff it drew and draw on top of it. So now we get a lot of kiwis making a pattern. Well, that's kind of nice. But all is good and well, but what if we don't want this to rotate around that top left? What if we want, essentially, what if we want this to move in a different pattern? Well, let's try a couple things. If we want it to be radial and look like it's making a circle, well, we need the origin point around which it's rotating and all the stuff that's rotating around it to be in the middle of the sketch, right? So that would be the same thing as taking the whole sketch and moving it over halfway to the half of the width over and half of the width down, and then let us draw our kiwis. So in order to do that, that's called a translate. Okay, translate just means move. So right above the rotate, let's go ahead and just use the word translate. Now if you haven't used this before, I suggest you looking up this term in the processing reference, which you can always select any one of these blue terms, right click on it and say find in reference. It'll pull up all the information about it. But translate just means move. So I'm going to move this by half of the width of the sketch over by half of the height of the sketch down. Now I happen to know the width and height is set to 900 by 600, so I could say, hey, 450 over, which is half of 900, and then 300 pixels down, which is half of 600. That would work just fine. A quick-hand way to do that would, you could always say, hey, width divided by 2 and height divided by 2. The advantage of doing that, it'll give us the exact same numbers here, but it's just grabbing kind of dynamically, it's grabbing whatever this value is, for, and that's calling that width, and the height is whatever this is. So if later on you change this sketch to a different size, this will automatically still be halfway across the width of the sketch and half of the height down. So it's a little smarter to do it this way. So just to reiterate what's happening now, before the rotation happens and before the arrays get drawing, we're just moving the whole sketch over and down. Then we're letting the arm rotate, and then we're drawing all the for loop of kiwis. So there we go. Now it's sort of a little more circular. And just to kind of make sure that this looks a little bit better, I'm going to set the Y location of the kiwis to be 0. So it's going to draw them at the vertical top of our sketch. And now when the arm rolls, it should look more like the arm of a clock. Okay. Now, if there's any confusion as to why this is working, using this rotate and translate, the best way to think of it is, without the translate in place, when we draw these, it's using the top left of the sketch as the place at which it's rotating around. That would be fine in some cases, except if we wanted this to be the arm on a clock or something of a circle, we're only seeing 1/4 of the whole sketch, right? It's like seeing one of 4 quadrants. That means three quarters of the time we can't see what's going on with our kiwis. So the way around that is to move the entire sketch, and every time you do a rotate or a translate or a scale, it's going to do that to everything in the sketch. We're going to move the whole sketch over and the whole sketch down. Okay, but to do that, we do the translate first. And again, translate's just the same thing as move. It's going to move one width divided by 2, or half the width over, half the width down. Then it'll do our rotation. Then it'll draw our kiwis. And so we get something like this. Okay, and let's fine tune it a little bit. Let's bring the kiwis in a little bit. Remember, that's this I times 50. We can say I times 20. We'll rerun that. Okay, maybe a little bit too much. We'll just say 30. Better. Let's, we'll, just like before, we'll move the background part out of the void draw. I'm going to put it up in the void setup. So that means the background will only draw once. And then everything that happens in the void draw will always draw on top of what was created last. So we have this sense of artifacts, or a trail of where things have been. Well, that looks kind of interesting. And now I want it to go faster. So instead of the rotational value incrementing by 0.1 degrees every single frame, let's say 0.9. 9 times faster. And our sketch is running, and pretty soon here we're going to have a nice full circle. As soon as it hits this point, well, now we've already been here, but that's okay. This is a good starting point for now. So those are a couple interesting things that we can kind of do with a for loop, and just as a little bonus, I threw in a translate and a rotate here to better understand this. Hopefully this was helpful, and I wish all of you well with your programming endeavors. All right, thanks.